In our previous discussions about thermodynamics, we've learned about how energy changes in chemical reactions. We learned that exothermic reactions release energy into their surroundings, and that endothermic reactions require energy input from the environment for them to succeed. Though this information helps us account for energy changes that we can measure in calorimetry, it doesn't tell us why a particular process or reaction proceeds in a certain direction. A process can be called spontaneous or thermodynamically favorable if it can occur without outside intervention. Some examples that we can be aware of include gases filling their containers. Let's say you start with gas molecules in one part of a container. They will spontaneously spread out as much as they can. Another example includes combustion reactions, where you could have something like a candle, where there's a complicated fatty molecule in the oil or in the wax burning to produce things like carbon dioxide and water. We could also have something like ice, a solid water turning into liquid water at any temperature higher than 0 degrees Celsius. And then there's other examples that are chemical examples that can also happen spontaneously. Consider this reaction. In this demonstration, I'm about to mix a whole bunch of solid barium hydroxide, octahydrate, which just means that it's barium hydroxide ionic compound crystals that have a ratio of 8:1 waters within those crystals. And all of those waters are in their solid form inside of that crystal. And then I'm also adding in a whole bunch of ammonium thiocyanate, also in its solid form. Now, at first, you might think that this is going to be, pretty boring because we just mixed together two white powders. But you'll see as I start to mix it that something weird starts to happen. So take a look. You can see that the two compounds now look like they're wet. So we can see some kind of liquid is forming. And I really wish I could let you guys sniff through this video, but something that you also smell is like that Windex type smell. We also see something very strange. This particular probe was a temperature probe, and you could see how the temperature dropped several degrees. Now, we can break down what actually was going on by looking at the chemicals that we had and seeing what we could possibly made in this reaction. Now, as I said just a second ago, we saw that the compound was getting wet. It's quite possible that these waters broke free into their liquid form. I also told you that I smelled ammonia, so we can see that ammonia was breaking free from this ammonium ion. And if it was reaching my nose, it was probably in its gaseous phase. And the leftovers are probably just leftovers, but if there was a bunch of liquid at the end, this barium hydroxide probably broke apart. I bet the extra H hopped onto these hydroxides to become even more waters. And the barium salts probably remained aqueous, but if they didn't, they could pair up with these thiocyanates. Now, what's cool about this is that this reaction was endothermic. And that's weird. You would think that energy being released to the universe is a much more common, spontaneous process. However, it seems like being exothermic is not the only thing that can help you be thermodynamically favorable. We call processes like this entropy driven. And what that means is that this is a process where we are increasing the freedom of choice of where molecules can be. Instead of being locked in a grid, our water molecules are free to flow around. Instead of being locked in a lattice, we have our ammonias free as a gas to expand and roam around. This type of, probability is called positional probability. The idea of positional probability works kind of like this. Let's say you have 4 little gas molecules or atoms inside of a container that has 2 sides. There's only one way to position all of the atoms or molecules all the way on the left. But let's say you want to move one of these molecules to the right side. You could move molecule number 1 over to the right, or you could move molecule number 2 to the right. You could move molecule number 3 to the right, or you could move molecule number 4 to the right. That gives you 4 possibilities instead of 1 possibility, where these 4 possibilities are far more likely to happen than my one-shot chance over on the left. This is even greater if you wanted to move 2 of the molecules to the other side. If you want to move 2 molecules over to the right-hand side, there are 6 different ways to do this. So it's like 6 times more likely to occur than our put everybody over on the left. Now, gases don't come in packages of 4 molecules. So I want you to imagine what this would be like with a mole of molecules. You would have infinitely more ways to arrange things so that the gases were spread out evenly between the 2 containers than to have the gases bundled up into a corner by themselves, effectively making disorder or mixing up or spreading things out way more physically possible than things being organized and together. Now, to apply this idea to exam style questions, what we need to do is we need to consider whether a process has a positive or negative change in entropy or disorder. We use the letter S with a symbol for change in front of it to describe how the disorder is changing in a certain process. For example, let's consider some carbon dioxide as a solid, which you can totally buy at the grocery store if you're over 18. That's dry ice. And as it sublimates, going to carbon dioxide in its gaseous form. Now, the gas has far more choices of where it can spread out to, so it has more freedom. So overall, the change in this direction is positive. So we would say that the delta S is a positive value. You could say the same thing for gases that are at different pressures. So let's consider nitrogen at 1 atmospheric pressure versus nitrogen gas at 0.01 atms. Obviously, this low pressure gas has a lot less force keeping it down, so the nitrogen molecules will be able to spread more effectively. This would be a positive freedom change. Now let's consider a salt dissolving. Here we have ammonium nitrate, which if you remember from the lab where we mixed salts with water to see if they were endothermic or exothermic, this particular guy gets really, really cold. However, as it dissolves and breaks into 2 different species, it now has twice as many places that it can be. When you increase the number of molecules that have freedom to move around, you have a positive entropy change. More particles means more choices, which means more freedom. In every single one of these cases, we have increased the amount of freedom that the molecules have. We've increased their position choices for their positional probabilities. The last example I have is about the number of arrangements that a molecule can have. Let's consider a molecule like methane versus one like propane. Now you might think, well, there's one of each, it should be the same, but that's definitely not true. You can look up the entropy values for each different chemical in the back of most textbooks. For CH4, at least in my textbook, our entropy value under standard conditions is 186 joules per mole Kelvin, where the propane is 270 joules per mole Kelvin. So why would the propane have a higher amount of intrinsic energy, or rather entropy? I like to imagine that a lot of this internal entropy has a lot to do with the number of electrons inside of a molecule. If you have more electrons inside of you, you have more areas where those electrons could exist. Therefore, more disorder inside of your molecule. So propane, being a much bigger molecule, would have a lot more choices for where the electrons could exist. So this is a lot of really interesting conceptual stuff. Make sure that you do all the practice questions available in your textbook so that you can really wrap your mind around how to predict entropy changes.